Hey there, in this recording I am going to discuss the Newton's laws and how you would understand them in terms of the pi-space theory. The pi-space theory is in pi-space physicstheory.com now. It has its own domain. Previously it was in a storytwig.com domain, and I've subsequently moved it. Now, in the documentation for the actual theory, I have a HTML section and a PDF. They're essentially the same versions of the documents, but one is in HTML and the other is in PDF. And the document I'm going to describe now is the Newton's laws document here. Isaac Newton in the Principia described his fundamental principles of physics, where he laid out the rules. Of how things work in our reality, what we would call classical physics, and he formulated 3 laws. Now I'm going to go through those 3 laws now. So now this is the PDF here. I'm just going to make it a little bit smaller, make it a little bit easier to look at, maybe just a bit bigger. So Newton's laws. So basically, in the Newtonian view of the world, which has held since it was proposed by Isaac Newton, he came up with 3 very good laws. He came up with his first, second, and third law. And I'm just going to go through each law, and I'm just going to say this. I'm going to map each law to pi space. I'm going to show how you can understand the pi space theory in terms of the Newtonian laws. Now this is a very important thing to do. I think in current physics there's a lot of focus on particle accelerators, and there's a lot of interesting theories of gravity put forward and so on. But in the pi space theory, the attempt is not to solve just the missing parts. The attempt is to produce a framework that works in both the classical view of the world, namely the Newtonian view, Bernoulli, the electromagnetism and so on, and the newer stuff, which is the 10 dimensions and the standard model. So it's very, very important that from my perspective, that the pi space theory can be described in Newtonian terms, because on a personal note, the Newtonian work for me is possibly the most intuitive of all the physics work that has been done to date, in my opinion, in that it is very intuitive, it's quite easy to teach, and for me personally, it just makes a lot of sense. So the first law is an object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same speed and in the same direction, and unless acted upon by an unbalanced force. And it's also called the Law of Inertia, and it was defined by Galileo. So much of Newton's work was essentially built on top of the work of Galileo, who came before him. So essentially, this is a reasonably straightforward thing to describe in pi space, because what we're mostly talking about are what I call the pi shells in pi space. A pi shell can be a single atom, or it can be a group of atoms, or it could even be an entire planet. But in this case, we're mostly just talking about a pi shell. Now, I've described in other lectures the pi space notation. We have an observer here, and atom, or pi shell, and we have some shrinkage in a certain vector. And essentially, if you were to map the Newtonian law, the first one, to this, essentially this just keeps moving in this direction unless acted upon by some outside force. It could be that it moves through gravity fields and will change direction, or it could be that it collides with another pi shell or another atom. So that's essentially the way to describe it in pi space. Very simple, just a simple diagram like that. The arrow is just there to help show that it's moving in this direction. If you understand the pi space notation, you don't really need to show that. But basically, this remains unchanged. Now, the directional component, which is a slightly more interesting question, is how does it know that it's supposed to keep moving in this direction? And in the pi space theory, the idea is that inside the pi shell, the space-time component inside the pi shell indicates the shortest wavelengths are in the direction that the pi shell is moving. So so basically, the pi shell itself remains a sphere, and gets smaller as it moves faster, and that the waves inside the pi shell itself, the material that it moves through, the fields that it moves through, remain constant as it moves in this direction, unless they move through altered fields and it changes direction, such as through a gravity field. So it's pretty simple. That's Newton's first law. Okay, it's probably the most trivial example, but it's pretty important to just describe it in pi space. Now, second law. This is probably the law that most people probably understand a lot better and know about a lot better in the real world, and it's so simple you can often sort of forget it's even a law, but it's Newton's law, and it's basically formally stated that the rate of change of the momentum of a body is directly proportional to the net force acting on it, and the direction of change in momentum takes place in the direction of the net force. Right? Now, that is quite elegantly described with the following formula here. F equals ma. So we move away from the idea of velocity, and in this case velocity is up here. This is what you would call momentum. An object traveling at a velocity in a direction, we say it has momentum. Now, when we talk about an object changing with regards to acceleration, we talk about force. So we go from force to from momentum, which is velocity based, to force, which is acceleration based. Now, one of the things that isn't tremendously intuitive in the Newtonian work, and this is what made life very difficult for Einstein when he tried to do his general relativity piece, was that the velocity component is reasonably straightforward. It's pretty intuitive. But the acceleration is the rate of change of velocity with respect to time. So we add a change in the velocity and we add a time component. Now, in the pi space theory, if you've studied it up to this point, or maybe you have or have not, it's pretty simple. An acceleration is a rate of change of area. So when a pi shell moves faster, it loses area at a particular rate, which is time based. And so what Newton did was he created the concept of acceleration, and it's a great idea, and it works, and you can do all these amazing calculations off it, and it's intuitive up to a point, but it becomes confusing because you have to subtract the velocities and you have to divide by time. And then in the Newtonian, in the relativistic space, it turns out that the acceleration isn't actually linear. So in the pi space theory, we have a few views on acceleration. One is that it's an area change of a pi shell with regard to time, and we know that time also is altered with respect to the clock tick is altered with respect to the size of the pi shell. So what we do in pi space is pretty simple. This is this piece I'm showing you here is from the advanced formulas. We keep the Newtonian of acceleration concept, which is what I wanted to do, and is not what Einstein did. He completely threw away the Newtonian acceleration idea, and he went on and created general relativity. But what I wanted to try and do was keep the acceleration idea, because it's so intuitive, right? I just felt that it would be better if it would be attempted to keep acceleration but add something to it in order to keep the Newtonian concept. So what I did was I added this value called alpha. Now what alpha is it's a calculation that one makes. I won't go into it in here, but basically if you go to the advanced formulas, you'll see that the alpha value is basically the slope of the rate of change of area. area change, and it's a value. So basically, at a lower value of velocity v, where v is much less than c, alpha turns out to be 1. So in other words, the Newtonian value turns out to be just as we had it before, and there's no change. So you can assume that for v less than c, it's 1. Now, as you move closer to v, close to c, the alpha value changes, and it depends on the range of values of velocities we're dealing with. So it's basically a slope calculation. It's in the advanced formulas. I'm not going to go into it here. Basically, the basic idea is it's a slope calculation. The slope is 1, where you have small values of velocity, and as you go up towards the near the complete compression of the pi shell, it changes to more like a 0 value. So in other words, as you try and push and push and push and try to accelerate an object, it becomes more and more difficult to accelerate a smaller and smaller object. Now, this explains, now there is a divergence in the ideas in pi space versus the Einstein approach. The Einstein approach says that in a particle accelerator, when you continue to accelerate something, the Einstein work states that the mass of the object grows infinitely. The mass component, and it's the mass component which causes the object to no longer be capable of being accelerated. In the pi space approach, we don't say that that's wrong. What we say is that the pi shell is getting smaller, and that the amount of area loss you can subject, the amount of force you can subject a smaller pi shell to, becomes smaller and smaller and smaller. So the analogy I would have is, as you push a pi shell up near the speed of light, it's like trying to accelerate. It's like trying to accelerate light. It's like when you've light in a room. Imagine trying to push light around with your hand. You can't do it. So essentially, the idea would be in pi space would be that as an object becomes closer to the speed of light, it becomes more wave-like. So you're trying to push a wave with an external force, and essentially, what I do in this formula here is just try to explain mathematically the idea of something getting smaller, and then the slope changing, and then as the slope tends to 0, you can't effect a force on it anymore. Therefore, the acceleration falls off. Now, the second part of the formula is to do with which isn't very well defined in the Newtonian work, I don't think. I mean, it's very intuitive. I mean, we know what mass is, and we know what weight is, and things like that. But in the Newtonian work, mass is mostly based around the weight of something under gravity. So it's already inside a force. Now, in the pi space theory, what I did was, there is the standard model of physics. This piece here you're looking at is from the standard model of physics that I've reverse engineered into pi space. And what I have done is I have mapped mass to a wave function, and I have said that the mass waves exist inside gravity waves. So the pi space theory states that mass exists within a gravity wave. It's a wave within a wave design pattern. And so that's the design pattern for mass, for gravity waves, and so on. So the idea would be you have waves inside waves. So that's the mass component, right? So you imagine a pi shell or an atom with more mass. It has more of these inner waves within the gravity waves. Now, so the more mass an object has, the more gravitational the greater the gravitational component of the mass waves. So the mass waves comprise the gravity waves. So they're intrinsically bound, and we see that in the Newtonian formulas, that it's the mass of an object which creates the gravity field around the object. So what we do is we draw inner mass waves inside a gravity wave. Now, so that's it would say for, hypothetically, we'd say 10 mass waves, just hypothetical. And then down here, we say 50 mass waves, yeah? So basically, it's a combination, we'll just return, it's a combination of the mass waves here with the acceleration, and the acceleration is an area change, which can be multiplied by this alpha value, which is 1, where the speed of light, where the velocity is much less than the speed of light, like 10 miles an hour or 20 miles an hour. The slope is 1. Alright, so that's the Newtonian work, and that's the force that an object projects. So that's if you have an atom, if you have like two cars, and if you have a car with a lot of mass, traveling at 20 miles an hour, and it hits another object and decelerates, it will project a lot more force than something with the same velocity and less mass. So we move on to the third part of the laws. This is really a very fundamental law. Again, it's basically it sounds relatively simple, but there's a couple of ideas in it that I need to explain in PySpace. And basically, Newton's law says, real simple, for every action there is an equal and opposite reaction, right? So force of reaction is equal to the force of the action, and we then say that the mass of A1 and M1A1 is equal to M2A2. So there's two components. There's the mass waves, and then there's this area change concept. So what we have is we can draw this using what are called absolute pi shells. So the idea is that instead of drawing these pi shells from an observer with a line, we draw the absolute pi shell, so we can see three pi shells of equal mass colliding with one another. You get them changing size equally, and that's your acceleration there across some pi shells. The rate of change of compression in the different directions. You've got the action, you've got the reaction. So that's it at its simplest. They're geometric laws. So then you move on to drawing this in a non-absolute pi shell. We do it in terms of an observer pi shell. So there's an observer pi shell, and we say how much of an area change for each of the pi shells. So these two diagrams are essentially equivalent. Here, this one here, and this one here, except that this one is drawn in terms of an observer. So these would be accelerations. So this is area change, increasing area change, larger area change, which would map to a smaller pi shell. And then we have then the idea of mass being different. So in these previous examples, the mass of each pi shell was the same. So let's say there's twice as much mass here as here, because there's twice as many pi shells. Well, then the acceleration here, this is half the mass, so it has twice the acceleration. So that's where they all have the same mass, but there's 4 of them, so there's twice as much mass. And this is sort of indicating a kind of a sort of the idea that the acceleration is different. And then we move on to the idea of our atom model, where we have things like carbon. We have like a pi shell that's made with carbon, and we have a pi shell that's made with lead. So basically, this one has more inner mass waves than this one, and you can see that this one has more mass, and this one has less mass. Even though there's fewer pi shells, there's more mass waves. Therefore, the acceleration is greater here, or the deceleration is greater here. The area change. So it all goes back to area change. So that's the idea of PySpace. We try to draw the diagrams in a very simple and intuitive way in order to cover the different cases. So that's all I'm going to do in this lecture, but I just wanted to give any interested reader a heads up into how to map the Newtonian laws, the 3 of them, into PySpace. Thank you.